Hello everyone. In the last video, we have seen what are the steps to solve a variational problem with moving boundaries. Okay. Now let us take one example. Find the shortest distance between the points 1a 1, 0 and the ellipse 4x square plus 9y square equal to 36. So you can clearly see here we are given one point, that is 1, 0, and the other curve is the ellipse, and we want to find out the shortest distance from this point to a point on this ellipse. Okay, so it is somewhat of the form: we have the point A, that is 1, 0. Okay, and we have this ellipse. So this will be what ellipse now? Suppose this point is 1, 2, 3, minus 1, minus 2, minus 3, and from here it will be 1, 2, minus 1, minus 2. Okay, so if I plot this ellipse, it will be on the x-axis, it will be this 3 and minus 3. It is the ellipse of this form, where this is minus 3 plus 3, 2, minus 2. Okay, and what we want to do is, from this point we want to find out the shortest distance on this ellipse. That means on this ellipse we want to find out one point such that the distance between that point and this point, whatever we get, it will be the minimum one. Okay, that means, and if I consider any other point other than that point, the distance will be more than this point, whatever we have found out. If you just observe the figure, you can easily make out that the point that we want will lie somewhere here, yes, or maybe here. Okay, so now let us calculate where we are getting that point. And the figure, it tells you that our point x0 comma y0, okay, is this, and whatever we want to find out is the point x1 comma y1. Okay, now observe that the first point x0 y0 is not moving. This point is fixed, and the point x1 y1, this point is moving on this curve. So we want to find out, from here this point is moving like this on this curve. So we want to find out at which point we have to stop, such that distance between this point and that point should be the minimum one, and that means it will give us the minimum distance, shortest distance between point and the ellipse. Okay, and therefore this problem falls under the topic variational problems with moving boundaries. So we have already seen the noted down the steps of solving such a problem. So let us start with the first one. It's clearly given that we want to find out the shortest distance. Hence, y comma x is equal to integral from x0 to x1 root of 1 plus y dash square dx. So this is the functional that we will be dealing with, such that y at 1 is equal to 0 and the other point, the point x1 comma y1 is moving on y equal to phi of x. Let us take this curve to be as phi of x, and what will be that? So y will be what? 36 minus 4x square divided by 9. So that will be root of 9 minus x square and 2 divided by 3. So y in terms of x. From this equation we will have to find out what is the curve phi of x. Okay, so we will write y in terms of phi in terms of x. So I have shifted all the terms that side, and that is phi of x is 2 by 3 root of 9 minus x square. So this is our curve phi of x, and this point is moving on this curve, and the first point, that is this, it is stable, it is not moving. Okay, so we will follow the steps that we have already noted down. The first step is solve the Euler-Lagrange equation for this functional and find out the extremal curve. Okay, so step 1, capital F in this case is given by root of 1 plus y dash square. Okay, and clearly from here this capital F is depending only on y dash, and therefore the extremals will be given by y equal to c1x plus c2. Okay, so Euler-Lagrange differential equation reduces to fy dash okay, in fact I can directly write it because we already know the form. So y of x is equal to c1x plus c2. Okay, and this is f of x c1 c2. It's a function of x, c1 and c2. Okay, then as per the procedure, step 2, step 2 we write the equations y at x naught is equal to xi at x naught, that is equal to f at x naught c1 c2. Okay, so and this is one equation, and we write a similar equation for x1. Y at x1 is equal to phi at x1 f at x1 c1 and c2. So these are the two equations that we write. If you see in the steps that we have already noted, you will see this. So let's write the first one. In our case, the xi of x, we don't have a curve as the first point is a fixed point. Okay, only phi of x is the curve that we are having. So since the point a 1 comma 0 is not moving and it lies. Okay, so we want to write y at x naught. This y at x naught, point x naught, what is our point x naught? 1 comma 0, equal to xi at x naught. So what will be our curve xi of x? The point is not moving, okay, but we know that this point is lying on the extremal, because what is the curve that we are trying to find? We are trying to find a curve such that the distance between this point and the other end point of that curve, along that if we travel, we will be traveling the shortest distance between the point and the ellipse. Okay, and I have already mentioned it in the last video that whatever points we are looking for, those end points will be the end points of the extremal. Okay, they will lie on the extremal as well as on the curve on which they are moving. Okay, but our initial point, this point is not moving, and therefore we will say that, and it also lies on the extremal. Therefore we have so corresponding to this first one, what we will get is y at x naught. So this capital F at x naught c1 c2 equal to y at x naught. This will be, what is f x naught c1 c2? It is nothing but this. So in this place, in this equation, we put x equal to x naught. But what is our point x naught? X naught is equal to 1. Hence here we get c1 plus c2 is equal to, what is y at x naught? So this at the point x naught. So this is the equation. And at the point x naught, meaning at x naught equal to 1, what it is? 0. So that is what we get. So c1 is equal to c2. That implies c1 is equal to minus of c2. And from the second condition, we will get, since the next point x1 y1 is moving on the curve phi of x, that is y equal to 2 by 3 root of 9 minus x square, we get, what will be capital F at x1 c1 c2? That will be c1 into x1 plus c2 equal to, so this phi at x1 will be, this is phi of x, we want phi at x1. Okay, so it will be 2 by 3 root of 9 minus x1 square. And we have already seen that this c2, it is minus of c1. Okay, anything we can use, c1 minus of c2 or c1. I will replace c2. So c2 is equal to minus of c1. So here what we will get is c1 into x1 minus 1 equal to 2 by 3 root of 9 minus x1 square. Then we go to the next step. Next step is writing the transversality condition. At x equal to x1, okay, because our left point, meaning the first point, it is not moving, and hence we will have only one transversality condition, that is at the point x equal to x1, that is the point which is moving on the ellipse. So the transversality condition is given by capital F plus phi dash minus y dash into capital F at y dash, differentiating f with respect to y dash and evaluating this expression at the point x equal to x1 equal to 0. Okay, so f is root of 1 plus y dash square plus phi dash will be phi of x is given by this. So we will have to differentiate this with respect to x. So when we differentiate it with respect to x, what we will get is 2 by 3 into 1 upon 2 times root of 9 minus x square into minus 2x. So this will get cancelled. So this is phi dash minus y dash. Y of x is what? C1x plus C2. If we differentiate this with respect to x, we get C1 into fy dash. Fy dash will be root of, this is f, differentiating it with respect to y dash, 1 upon 2 root of 1 plus y dash square 2 y dash, and then evaluating this expression at x equal to x1 and equating it to 0. Okay, so root of 1 plus y dash square plus 2 by 3 minus 2 by 3 into x root of 9 minus x square minus c1 y dash upon root of 1 plus y dash square, evaluating it at x equal to x1 equal to 0. So now we will put x equal to x1 in this place. So first, root of 1 plus y dash square. Okay, y dash is what? From this expression, y dash is equal to c1, and y dash at x1 will be what? It will remain c1 as it is. So this will be 1 plus c1 square plus minus 2 by 3 x1 root of 9 minus x1 square minus c1 into, what is y dash? Y dash is c1, and evaluate the y dash at the point x equal to x1, that will remain c1. Okay, so this is c1 by root of 1 plus c1 square equal to 0. So now we will simplify this expression. So let's multiply this inside. Root of 1 plus c1 square plus minus 2 by 3 x1 c1 by root of 9 minus x1 square minus c1 square 1 upon root of 1 plus c1 square equal to 0. Okay, so you see here this term is multiplied only for this bracket. Okay, and then we have this term. So I want to remove the denominator, so we will have to take the LCM, do the cross multiplication and write the simplified term here. So this will be root of 1 plus c1 square the whole square, so it will be 1 plus c1 square into 3 into root of 9 minus x1 square minus 2 x1 c1 minus c1 square into 3 into root of 9 minus x1 square equal to 0. So root of 9 minus x1 square minus 3c1 square plus 3 minus 2 x1 c1 equal to 0. So this will give us 3 root of 9 minus x1 square equal to 2 x1 c1. But clearly from here in step 2 we have seen that root of 9 minus x1 square is equal to 3 by 2 times c1 into x1 minus 1. So I will substitute this in the equation. Okay, so root of 9 minus x1 square I will write it as 3 by 2 into c1 x1 minus 1. This will be equal to 2 times x1 c1. So this will be if we take this 2 here, this will be 9 by 4 c1 into x1 minus 1 equal to x1 c1. So now we divide the equation throughout by c1, assuming that c1 is not equal to 0. Okay, because if c1 is equal to 0, then what happens is here then it will tell us that it is nothing but because if c1 is equal to 0, then this y of x will be equal to c2, and the point 1 comma 0 is lying on the extremal, so that will imply that this c2 is equal to 0. So y of x is equal to 0, and that will be the whole of x-axis, and therefore the curve will be nothing but the line from this point to the point on the ellipse, that is this. Okay, so where under the condition c1 not equal to 0, what we will get is 9 by 4 x1 minus x1 is equal to that will imply x1 is equal to 9 by 5. So we have got the first point, x1 equal to 9 by 5. Now to find out the point y1, okay, because the point x1 and y1 they are lying on the ellipse, okay, so y1 will be 2 by 3 root of 9 minus this x1 square, okay, as we have seen here in the equation. Here what was the equation? Phi at x1, that is y1, is equal to this at the point x1, okay, so phi at the point x1 will be 2 by 3 root of 9 minus x1 square, that will give us the point y1, which will be 2 by 3 root of 9 minus y1. So this will be that will imply y1 is equal to 8 by 5, okay, so 12. Now we have got the point x1 y1. We also want to find out c1 and c2, okay, so from this equation if we substitute x1 in this equation, what we will get is 3 into, let's name this equation, 12 by 5 into 2, so divided by x1, so that will be equal to c1, so that will imply c1 is equal to 2, okay, and we have already seen that c1 is minus of c2, and from here it implies that c2 is equal to minus 2. Therefore y of x is equal to c1x plus c2 is equal to 2 into x minus 2 x minus 1, and the question asked was find the shortest distance between the point a1 comma 0 and the ellipse, okay, so now we have the points a1 comma 0 and b is equal to x1 we got it as 9 by 5 and y1 we got it as 8 by 5. So distance this you already know the distance formula, so x2 minus x1 the whole square, 9 by 5 minus 1 the whole square plus y2 minus y1, or in, yes, we have considered this as x1 y1 x0 y0, so y1 minus y0 the whole square, so that is 8 by 5 the whole square. So this will be equal to, so this will be 80 by 5. Let us look at one more example. Find the shortest distance between the parabola y equal to x square and a straight line y equal to x minus 5. So again the question asked is find the shortest distance, so the functional will remain the same. Okay, so as we have solved the first problem, you have seen that we follow the first step, second step, third step, and once we get all those equations, in the fourth step what we do is we solve those equations simultaneously to find out the values of x1, y1, c1 and c2. Okay, because in that case, in the first problem, our first point x0 y0 was fixed and only the next point was moving. Okay, so in terms of the graph that we have already seen in the last video, it will be xi of x, there is no curve xi of x because the point x0 y0 is not moving, and we only had the curve phi of x, which was the ellipse, and that second point was moving on the ellipse. Okay, but now if you read this problem, find the shortest distance between the parabola y equal to x square and the straight line y equal to x minus 5. Okay, so y equal to x square, so the figure will be, this is the graph, y equal to x square and line is y equal to x minus 5. So the line will be 5 and this is minus 5. It will be this line, and we want to find out the shortest distance between this curve and this line. So what we will have to do is first take the functional and find out the curve, and then find out which are those 2 points through which that curve is passing, such that once we travel on that curve which is passing through those 2 points, we will get the shortest distance between this curve and this line. Okay, and clearly from the figure, in this case there are two curves, xi of x and phi of x, and the point x0 y0 as well as the point x1 y1, both the points are moving. Okay, so Vy of x is equal to integral from x0 to x1 root of 1 plus y dash square dx, such that the point x0 y0 moves on x square equal to y. This is the curve, and let's call this curve as xi of x. Okay, and the point x1 y1 moves on the curve y equal to x minus phi, and let's call this curve as phi of x. So what you will have to do is, I will not solve this problem in detail. So you already have the procedure to deal with the moving boundary problem. So follow the steps and come to the final answer. Note that in this case, when we write the transversality condition in the third step, okay, because both the points are moving, we will have two transversality conditions, that is the one corresponding to the function phi and the one corresponding to the function xi. And then once we get all those equations, in the last step we have to solve those equations to obtain the value of x0, y0, x1, y1 as well as c1 and c2.